Throughout Unit 7, we need to refer back to this discussion question of what do you think happens to the mass of a substance in a chemical reaction? Now, in a chemical reaction, we are going to have the reactants and the products. So, whenever we have the reactants and the products, the mass should be the same on both the reactant side and the product side. This is going to refer back to the law of conservation of mass, that mass cannot be created or destroyed, it is only changed. And we have to make sure that the chemical equations are a representation of that. So, talking about the basics. A chemical equation is a representation of a reaction that takes place. We're able to see the reaction as either a formula or in a word form. Here are some of the symbols that you'll see inside of an equation. The first one is going to be an arrow. The arrow by itself means to yield or to produce. If we have an arrow with a delta or the word heat above it, that means that the reaction requires heat in order to progress. An arrow with an MnO2 or any compound above it is going to be called a catalyst and allows the reaction rate to be increased. This means that the reaction is able to happen faster or it is going to lower the activation energy in order for the reaction to take place with less energy. If we have an S after a compound, that means that the compound is going to be a solid. If the compound is followed by an L, this means that the compound is a liquid. If the compound is followed with a G, that means that the compound is a gas. And if the compound is followed with an AQ, that means that the compound is going to be aqueous. And keeping in mind that the AQ, meaning aqueous, means that it is a solid dissolved in a liquid, very similar to the idea of salt water. Now, what does our chemical reaction tell us? And it is able to tell us quite a few different things. The first is that the amount of reactants and products that are formed. The second is going to be the ratio of reactants and products. Now, remembering that a ratio or ration is a relation between two amounts. And you're able to think of this in chemistry similar to those found in cooking. If we have 2 eggs and 1 cup of flour, can make 1 cake. Now, the ratio of eggs to cake is going to be 2 to 1, which means that we need 2 eggs to make 1 cake. And this is going to be a ratio, very similar to the idea of cooking. If I double the amount of cakes that I need to double the amount of the ingredients that I have. And then we're going to use this to create a ratio in order to relate the moles of one substance to moles of another. And this is going to create a mole ratio that we're going to use a little bit later. And then if the reaction is reversible, and this is not always possible. And how we're able to tell that is that if we see arrows pointed in the opposite direction, this means the reaction is reversible. Now, the law of conservation of mass, the really large idea in chemistry. Whenever we look at the chemical reaction, it needs to follow the law of conservation of mass. And this law is a large theme throughout chemistry, so it is going to pop up quite a bit. So just kind of remember that this law states that the mass cannot be created or destroyed, it only gets changed. So the reactants will form a new product. The mass at the end is going to be the same, but it just may look slightly different than what it started out to be. Now, how do we use this? What this means for a chemical reaction is that the number of atoms on the reactant side must equal the number of atoms on the product side. And so, what this is going to lead us to is going to be the idea of balancing a chemical equation. So, not only do we have to have the same number of atoms, but we also have the same number of each type of atom. So, if I start with 5 silver atoms, I need to end with also 5 silver atoms. So if we start with 5 atoms of carbon, we need to end with 5 atoms of carbon. Now taking a look at this chemical equation, we have H2 plus O2 forming H2O or water. Now what we're going to need to do is that we need to balance the chemical equation. And we're going to do that by placing coefficients out front of the chemical symbols. So coefficients are going to be out front of the compound, and the coefficients are going to multiply the number of atoms in that compound. Now, really big thing to remember is that the subscripts in a formula cannot be changed. So those subscripts are always going to be there. The only thing that we're able to change is going to be that coefficient, which is going to be a large number out front. So for example, a coefficient could be 2. And so this means that everything I would end up with 4 hydrogen atoms. That 2 is going to multiply inside of that compound, multiplying those subscripts for a total number of atoms. Now let's go ahead and take a look at a few examples. So we have our 2N2S4. So counting out our number of atoms that we have, this 2 is going to multiply out right here. So we're going to end up with 4 nitrogen atoms. The same thing will happen with the other subscripts. So 2 times 4 is going to give us 8 sulfur atoms. Taking a look at our next one, we have our 2MgCl2. Now remember, if I do not have a subscript, I assume that I have 1. This 2 is going to multiply the magnesium to end up with 2Mg. This 2 will also multiply the chlorine that I have originally 2 of for a grand total of 4. Looking at our next one, we have 4CO. We have 1 carbon, 1 oxygen. This 4 is going to multiply out for 4 carbon atoms and multiply the oxygen as well for 4 oxygen atoms. Let's keep on going. We have our CBr4, coefficient of 4 out front. The 4 will multiply everything, so 4 carbon. And then 4 times 4 for the bromine will be a total of 16. Looking at our KF, 3 times 1 will be 3. 3 times 1 will be 3. So 3 potassium and 3 of the fluorine. Taking a look at the last example on this page, we have our 2 calcium atoms with that coefficient out front. Originally, we have 2 of the chlorine, but that coefficient of 2 will multiply it. So we'll have a total of 4. And that is going to be how we look at using our coefficients in order to make sure that the number of atoms is the same. Now, taking a look at a little bit more of a difficult set is that we are able to have different compounds within the larger compound. These and everything are going to be known as the polyatomics. And most of the time, we are able to treat the polyatomics as a single unit. So we don't have to break up each individual atom if the polyatomic is the same on both sides of the equation. Now let's go ahead and take a look at our first one. We have our MgNO2 2. Our coefficient of 2 will multiply the magnesium. I have 2 of the magnesium atoms. Now, this 2, the coefficient of 2, is going to multiply this outer number of 2. So this NO2 inside this right here, I do not want to change. So this 2, the coefficient of 2 is going to affect the outside 2. So we're going to end up with a total of 4 NO2 units. Let's take a look at another example. We have our 3PbSO42. This 3 will multiply our lead, end up with 3 atoms of it. Now, the SO4, because it is in parentheses and a polyatomic, we are going to keep it together as a single unit. So this means that this 3 is going to multiply the 2 on the outside. This means that we are going to end up with 6 units of our SO4. Taking a look at our next example, we have our NH4Cl with a coefficient of 2 out front. Now, even though the NH4 is not in parentheses, we are going to assume that it is. So we have 1 unit of the NH4. This 2 on the front is going to multiply that 1 unit of NH4 in order to get 2 units of the NH4. And this 2 will also multiply the chlorine as well in order to get 2. Next, we have our 2NaOH. Now, our OH is a polyatomic as well, so we can assume that it is a unit. We have 1 OH. This 2 will multiply our Na in order to get 2 atoms of Na. And then R2 will also multiply our OH by 2 as well to get 2 units of the hydroxide. Now that we know the basics for counting our atoms or polyatomics, let's get into the idea of balancing chemical equations. So our first step is that we're going to write the unbalanced equation. We are then going to count the atoms of each element on both sides, remembering that a polyatomic ion that does not change on either side can be counted as a single unit. So we are going to keep our polyatomics together if they are the same. We are going to add coefficients in order to balance the number of atoms for each element or polyatomic, and make sure that all of the coefficients are in the simplest number ratio. Now, as long as we balance the chemical equations correctly, this last step may not be always necessary. Let's go ahead and take a look at the first example. So we have our Na plus Cl2 forming our NaCl. So sodium plus chlorine forming sodium chloride. First off, we're going to separate this down the middle of our arrow. We are going to have our NaCl, NaCl. And on each side, we are going to count up the number of atoms that we have. So on the reactant side, we have 1 sodium and 2 chlorine atoms. On the product side, we have 1 sodium, 1 chlorine. And so what we may notice is that the chlorine atoms do not match up. I'm not able to randomly go from 2 chlorine atoms to 1 chlorine atom. And so what this means that this is an unbalanced chemical equation and that we need to fix that in order to be in line with the law of conservation of mass. Now, we're not able to change subscripts, and so the only thing we're able to do is that we are able to look at our coefficients. So what we have to think is what coefficient can go in front of my NaCl in order to make 2 chlorine atoms? Remembering that the coefficient is going to multiply. So that means that a coefficient of 2, this is going to multiply our chlorine by 2. So I will end up with 2 chlorine atoms. However, this 2 is also going to multiply our sodium as well. So we are going to end up with 2 of our sodium atoms. So by balancing out the chlorine, we unbalanced our sodium, and we need to go back and fix that. Now, the coefficient that is going to go out of our Na is going to be a 2 as well. So that will multiply my number of sodium atoms by 2. So I end up with 2 sodium atoms on the reactant and the product side. I end up with 2 chlorine atoms on the reactant and product side as well. Now, whenever we have a blank, we are able to fill this in with a 1, or we are able to leave it blank as well. Let's take a look at another example. We have our Zn plus HCl forming ZnCl2 plus H2. So zinc plus hydrochloric acid forming zinc chloride plus hydrogen gas. Let's go ahead and balance out this equation. So first thing that we're going to do is that we're going to split this down the middle. We have zinc, we have hydrogen, we have chlorine. And we're going to count these atoms on either side. On the reactant side, I have 1 zinc, 1 hydrogen, 1 chlorine. On the product side, 1 zinc, 2 hydrogens, and 2 chlorine atoms. And so what we may notice is that the hydrogen and chlorine do not match, so we need to balance the chemical equation. On the reactant side, I only have 1 hydrogen and 1 chlorine, and I need to get those to 2. So what coefficient can I place out front of our HCl in order to change those number of atoms to 2? And if you're thinking that we can place a coefficient of 2 out front, that would be correct. This 2 is going to multiply the hydrogen, so I end up with 2 hydrogen atoms. This will also multiply the chlorine as well in order to get 2 of the chlorine atoms. Now, by placing that one coefficient, we have balanced the overall reaction. We have 1 zinc on either side, 2 hydrogens on either side, and 2 chlorines on either side. So this reaction is completely balanced now. Now, with those blanks, we can leave them, or we can go ahead and just put in a 1 as a placeholder. Taking a look at another example, we have our KBr plus MgCl2 forming KCl plus MgBr2. We're going to go ahead, we're going to separate this down the middle. We have potassium, we have bromine, magnesium, and our chlorine. And we have that on either side. Now, counting out the number of atoms, I have 1 potassium, 1 bromine, 1 magnesium, and 2 chlorines on the reactant side. On the product side, I have 1 potassium, 2 bromine, 1 magnesium, and 1 chlorine. So this means that the bromine and chlorine are not balanced. So we need to go ahead and fix that. Now, how you start this off doesn't really matter. I typically like to start on the reactant side. So, in order to balance out the bromine, we'll need to place a coefficient out front of our KBr in order to get 2 of the bromine. Remembering that the coefficient multiplies, we are going to place a 2 out front because this 2 will multiply the bromine. I will end up with 2 of the bromine atoms. And then this 2 will also multiply the potassium as well to get 2. So I balance out the bromine, but I unbalance the potassium. Now fixing the potassium, I need to place a 2 out front of our KCl. This will fix the potassium to 2, and this will also change our chlorine as well to 2. So now if we take a look at our numbers, all of our atoms will match. We have 2 potassiums, 2 bromines, 1 magnesium, and 2 chlorine atoms. These remaining blanks, we're able to go ahead and fill in with a 1. Taking a look at the next example, we have our CaOH2 plus HI forming our CaI2 plus H2O. We're going to go ahead, we're going to balance this. Counting out our number of atoms, we have calcium, oxygen, hydrogen, iodine, and we have this on either side. We have one calcium atom. Now, for counting up our number of oxygen, we need to remember that this 2 on the outside distributes inward. So we end up with 2 oxygens. We end up with our number of hydrogens. So from our OH2, we have 2 hydrogens. But we also have this one hydrogen from the HI. So we have a total of 3 hydrogens that we have to work with. And then I have one iodine. On the product side, I have one calcium, I have one oxygen, I have 2 hydrogens, and I have 2 of the iodine. Balancing this out, let's focus on the iodine first, just because it is the simplest to fix. In front of our HI, we're able to go ahead and place a 2. This will multiply the hydrogen and the iodine. So I end up with 2 of the iodines. Now, whenever looking at this, we do need to be careful when counting up our number of hydrogen atoms again. So remember, I have 2 hydrogen atoms coming from our OH2, and I now have 2 hydrogen atoms coming from the HI. So adding these together, I have a total of 4 hydrogen atoms. Now taking a look on the product side, in order to balance this out, I need to fix the number of hydrogen and oxygen. If I place a 2 out front of the H2O, this will end up with 4 of the hydrogen atoms, and this will also multiply the oxygen as well in order to get a total of 2. So if I take a look at our total number of atoms, we are all matching on either side. So our coefficients will be 1, 2, 1, 2. Taking a look at another example, we have our Cu plus O2 forming our CuO. Splitting this in half, we have our Cu, we have our O, our Cu, and our O. Counting up our total number of atoms, 1 copper, 2 oxygens on the reactant side, 1 copper, and 1 oxygen on the product side. We'll notice that the oxygen is unbalanced, so we're going to go ahead and fix that first. Place a coefficient of 2 out front of our CuO. This will multiply the copper by 2, and this will also multiply the oxygen by 2. So I end up with 2 coppers and 2 oxygens on the product side. The oxygens now match, but the copper does not. So we need to go ahead and place a coefficient of 2 out front of our copper on the reactant side in order to change our number of copper atoms to 2. Taking a look at this, all of the atoms are now balanced, and we're able to place a coefficient of 1 in front of our O2 as a placeholder. Taking a look at the last example that we have our MgNO3 2 plus NH42SO4 forming MgSO4 plus NH4NO3. All right, so this does look like an extremely long equation in order for us to balance, but one of the things that we should notice is that a lot of the elements in this are going to be polyatomics, which we're able to keep together as a single unit. So this will save you a lot of time if you're able to recognize this pattern. We'll go ahead. Our first one is going to be our Mg. So we have our magnesium on both sides. Now, what we should notice is that we have our NO3, and our NO3 is the same on both sides, so we're able to keep it together as a single unit. So NO3. Then we have the NH4, which we should also notice is the same on both sides. So this is our NH4. And then we also have our SO4, which is the same on both sides as well. So we're able to keep the SO4 together. And we're going to have the same thing on the product side as well. Counting up our number of atoms that we have one magnesium, we have two units of our NO3, then we have two units of our NH4, and we have one unit of our SO4. On the product side, I have one magnesium, I have one unit of the NO3, I have one unit of the NH4, and I also have one unit of the SO4. So our NO3 and our NH4 are going to need to be fixed for our number of units. Now, luckily for us in this reaction, we need to fix the product side first of our NH4 and NO3. We each need to have 2 units for these, so we can place a coefficient of 2 out front of our NH4 NO3, and this is going to multiply the NO3 unit by 2 and also multiply the NH4 unit by 2 as well in order to make everything match. Now we're able to go ahead and place ones in as placeholders in these leftover spaces for the coefficients, and we have balanced this equation. So making sure that whenever we have a polyatomic on both sides of the equation, it is going to be extremely helpful to keep that together as a single unit in order to save time when balancing.